Sweet. Yeah. All right. Well, Martin, just wanted to say thanks for taking the time to meet with me. Obviously, I met you last year in Hawaii at a magic show of all places. Turned out we were both going to the same conference the next day, ICML. Sort of bumped into you and we had a chat, and I kind of found out that you were working at DeepMind in the control team lead there. And obviously we kind of hit it off because we both like magic and robots, I guess, was the was the start of it. And yeah, I was just saying before, I hadn't really been to a conference pre-COVID, but for me, I really enjoyed last year. It's my first one since COVID, and because it kind of just reminded me, like, the opportunity to meet sort of amazing, interesting people like yourself. But it also kind of gave me a good reminder of how much I loved magic. And so I don't know if you end up watching one or not, but usually the way that I start this interview is with a bit of an icebreaker. So normally I ask the guests what their favorite hobby is, their favorite music genre is, and their favorite food is. But seeing as I know that you also love magic, I thought we could do a sort of a special version of that today. And I've never done a remote magic trick before, and so you're the first.
Okay. Wow.
And so if this doesn't work, then I'm going to cut it out of the recording.
Okay.
But,
That's good.
sorry,
Fair
just
enough.
going to chuck this up here. So hopefully, yeah, you can see that. So I've got two decks here. We'll take the blue deck. Just going to give it a bit of a shuffle. Now what I want you to do is I'm just going to riffle through it, obviously, because you can't really reach through the screen and pick one out, but I want you to just sort of say stop for me.
Stop.
There? Okay.
Yeah.
Take that card. The first card is the 6 of spades. All right, just going to chuck that down here. You can still see that. And we're going to do this 3 times.
All right.
So we'll go again.
Stop.
Yep. Second card is the 2 of diamonds. Chuck that there. And then the last one.
Stop.
Last one is the 3 of clubs. They're good cards. That I can tell already. They're excellent choices, Martin. Now, so got a pen here. Now, do you have a favorite hobby, Martin? Obviously, anything you like to do, like when you get outdoors or anything like that. I'm going to write it on the card.
It's skiing.
Skiing. And now, a favorite music genre? Maybe, I don't know, anything you like to listen to while you study or while you work?
Classical music.
Classical. So we got classical and skiing. So far.
Yeah.
And then, any favorite food or treats? Any guilty pleasures? Anything like that?
Chocolate.
Chocolate. Any particular kind of chocolate? Any brand? Is there a brand you like?
I'm well, the most simple chocolate.
Any
It's called
chocolate?
milk chocolate. In Germany, I don't know if this is an international expression. With
Yeah.
not too much.
Chocolate. Milk chocolate. All right, I'll write milk chocolate. We got milk chocolate.
Perfect.
Classical and skiing. All right. Now, what I have over here in this red deck, what I've actually done, so you see it's all red. All the cards are different. You can see that.
Okay.
What I've done is I've actually gone through and I've written a whole bunch of random hobbies, foods, music genres in here. And what I'm going to do is I'm going to pick out the cards that you picked here. So you picked the 6, the 6 of spades, the 2 of diamonds, and the 3 of clubs. So I'm going to go through here and find those cards. We've got the 6. I'll place that one here for now. We have the 2, which you can see.
Oh, not bad.
And I have a bit of a problem here because you can see I wrote chocolate on the 3 of spades, but yours is 3 of clubs, right? But if we just give that a bit of a shake,
Oh,
what you can see here is that's the Ritter,
it's a
Ritter
spot.
Sport, the Ritter Sport milk chocolate. But unfortunately, mentalism did not work all the way because I put mountain bike riding for the 6 of spades. Now,
Which is, yeah,
if you had picked, for example, like the 6 of diamonds, you would see that says R prop on it, right? Which I guess may
yeah.
be a hobby of yours. But but the funny thing is, though, is if we look through this deck, you'll see that every single other card is actually R prop. So
Wow, very cool.
the 3 cards we picked out of the blue deck were the only 3.
Wow.
There we go.
Ooh,
2 for 3, I guess. I'll take it.
great opener. And skiing and mountain biking are basically mentally the same in my mental map.
I
So,
I
so
thought
I,
I
I could
thought
have said both.
I never really done a mentalism trick before, and like I was trying to prime you with talking about mountain biking before we started, but obviously it didn't work. All right,
I think this was probably the reason why, as an old magician, why I
you
deliberately
knew,
choose skiing,
yeah,
without lying, because I also like skiing. So
yeah. Oh well, that's funny. Um, you can thank Clara as well for giving me a bit of insights into your favorites.
I was thinking like the Alpenmilk. That's a bit probably too close.
Yeah. Let's get started, eh? So you've had a very interesting career, and so far it's still very much going. You actually work heavily in the field, which I'm super interested in, which is robot learning. And what I'd like to do though is just go back to the very start. So I did a bit of research into you, and probably one of the first things I found was some old German magazines. And in the you probably know this is going in those magazines were assembly games that you had built when you were in high school. Um, can you tell us at what age it was that you sort of knew that you wanted to go into computer science?
I think it was about the age of 13, 14. At that time, computers were very rare. Personal computers at home were very rare, but it was the dawn of that. So it was the beginning. And an uncle of mine was a high school teacher, and he had access to a computer. He invited me over to his place. I was taking the bus for an hour, which was an adventure at that time, uh, also. And then we just started to program. So he told me what I can program. Uh, uh, so taking away matches, so that at the end the computer always wins. You can take an arbitrary number, and stuff like that. And so this got me into thinking and programming. There was a small handbook where I can start with. And then whenever he came to visit us, he brought his computer with him. And so I spend the weekend usually sitting and just programming. So that
Writing
was
assembly code.
writing assembly code, yes.
Very.
Assembly code, that was a bit later, because when I then bought my own computer, that was a Sinclair ZX81.
Mhm.
And this one was nice because you could easily program it, but it was also very slow. And the only way to get a game, like an arcade game, done is to write your own assembler code. So
Mm.
I actually looked what I can do, then started my first. You could literally poke numbers into the memory that you could run then, and these numbers corresponded to assembler um, codes. assembler operations. And so I poked in the numbers and then saw some tiny little points on the screen, could move the points, and from that on, it was basically the challenge to write a game about that.
That's so cool. I mean, it's just, I honestly just sound like it's even hard for me just to even appreciate that kind of programming at, you know what I mean, at that such early levels. Because, you know, by the time I started programming, you know, it's just you've got so many more advanced tools at your fingertips, right? Like just being able to move a pixel, like the amount of effort that goes into doing that with assembly code, yeah, it's crazy.
Yeah.
Um,
Yeah, and in addition, at that time, getting information about that was pretty difficult because the internet wasn't there, at least not for me, wasn't available. And ordering a book like the assembler code for Z80, that was, first of all, it was very expensive at that time, and then ordering a book took about 8 weeks until you get
yeah.
it finally.
So could your uncle program then? Did he teach you or?
So I got basically this book, and then the program language was Basic,
Yeah.
and then it was the concepts were very simple, like an if statement, the for loops. That was very easy to understand. So I just learned it by doing
Mm.
and being fascinated by making it work.
So I was thinking about it, and I was wondering, like, you know, because obviously, in some ways, you started your career with games, but that's definitely not the last time you worked with games. I won't give too much away, but I was just thinking, how did you find this sort of like hands-on technical experience at such a young age? How do you think that affected your later work in machine learning and views on like algorithmic efficiency and optimization?
Uh, I think it was basically it was just an expression of my being. I always wanted to be an inventor. First, before I got into computers, I was doing electronics, and this always fascinated to do something by thinking, then creating it by hands, working with wood or so. So I don't necessarily think that it was that I got into computers and then this influenced my career. I think it was basically probably the other way around. It was my personality that I want to do this stuff. And with computers, you can invent anything. This is so fascinating about this computer language. They are unlimited what you can do on the screen. And so basically this was just an expression of my wish to be creative in
So
some sense.
like a canvas of opportunity for you.
Yeah, that's nicely
So
said. Yeah.
so I you went on then to do Diplom Informatica, which I learned is German for computer science. Can you tell us about that time of your life and what it meant for you?
Yeah, so after I got into computers, for me it was clear that I wanted to study computer science, and one of the best schools in Germany was Karlsruhe. So I applied there and happily got in, and I knew a couple of people who were there from my hometown. So I knew basically what to expect. So they have a very sound mathematical courses at the beginning, which were kind of difficult to pass. So I knew when I came there what to concentrate on if I really wanted to do that. But then I think from the very first minute, I was kind of fascinated by the machines there. Also going back a bit more to the lower levels of closer to assembler, closer to electronics, seeing it work in some practical courses. So I also remember that every time when a new semester started, I was very excited to see what courses come next. So I really enjoyed studying there.
Yeah, I suppose that's a good way to know you're doing the right thing if you're excited to see the syllabus.
Yeah.
um, Now, there's, you know, off killing off magic. I think that you could say there's a certain magic when you see a reinforcement learning system or agent come up with a novel way of doing something that maybe humans haven't thought of or done before. What is your favorite explanation of reinforcement learning? Like when someone asks you what is reinforcement learning, what's your favorite explanation?
I think probably my favorite explanation that I give in talks is usually riding a bike, because riding a bike is something that you cannot
Not
directly show
skiing?
to a.
It wasn't skiing?
You got me. But I actually, in one of my lectures, in my early lectures, I had a skier, a robot skiing as the example of reinforcement learning in a technical sense, because I thought, yeah, maybe biking of a robot is too far away, but having a robot with skis, I think I found a picture in the internet. So I actually used skiing as an example in my courses.
There you
But
go.
when I explain to laypersons, I explain by biking, because it's kind of obvious. If you fall down, you hurt yourself, you see something has gone wrong, and if you can go without falling, you know that you have managed the job. But
Yeah.
nobody ever can tell you how to use your muscles to do that.
Hmm.
And the only way to do this is kind of to learn this by yourself.
Just, I suppose, with falling on the ground, you just hope that you're sample efficient, I suppose. You know what I
Yeah,
mean?
exactly.
You want to be yes. So in your master's thesis, you developed Resilient Back Propagation Algorithm, RPROP, which was a huge contribution to the field, and even today is among your most cited publications. Why do you think RPROP was so impactful at the time?
I think the simple explanation is because it was probably the best algorithm at that time for batch supervised learning.
Mhm.
So that was the time when it was in 1992. A lot of people got interested in neural networks again, in multi-layer perceptrons. And then the typical gradient descent rule obviously has flaws. You have to look for the learning rate, which is either
Yeah.
too small or too big. And so there were a couple of suggestions. Um, SuperSAP at that time, QuickProp, then second order methods. But all of them basically kind of scaled the gradient. And RProp had the other idea of not looking at the gradient per se, but actually only looking at the sign and then adapting the size of the actual weight step according to the sequence of signs that you observe, which is basically what, if you think of it, what you want. And then what I was also surprised is that it worked very well. So it was either better or on par with the best adaptive learning rules. Plus, there were no parameters that you have to tune. So it basically always worked out of the box. And this is still some property that I'm keen to have in all the algorithms, because kind of tuning parameters that very often kind of uh, destroys the effect of a quick learning. If you have to repeat the experiments over and over again to find the right parameters, then you might as well just apply a slower learning method for a longer time. So, and RPROP was very robust with respect to parameter choice.
And I suppose, like, looking at sort of the core theme of some of that work, adaptivity and learning algorithms, I guess. How do you think that influenced your career trajectory from that point?
Um, I think it influenced it in the way that it was a competition. There were already some algorithms around.
Mm,
So basically, the only thing you didn't have to come up with a big explanation, but pure numbers could show that you are right.
yeah.
Uh, and I think this is still something at that time I wasn't very keen to give speeches, or I wouldn't have never have done the podcast
Yeah.
like this. I was rather a quiet person. So having something where you just show the numbers and it's convincing, that was very much fitting to my personality. So
I guess
competition is good.
that's like the allure of having those, like, benchmarks and those sorts of things, right? It becomes, as long as they're the right benchmarks, then
Exactly,
yeah.
exactly. Yeah.
Um, so after your masters, you obviously went to do a PhD. How did you make the decision as to what you wanted to do in your PhD?
So at my institute at that time, we were there were some people who were looking into playing board games already. And the first solution was by supervised learning. But at that time, around that time, they got excited by Tesauro's work of backgammon, which was able to learn backgammon from just self-play. And they tried to bring several similar approaches to board games. And I was really fascinated from that perspective. But I didn't want to apply it to board games because this was already done at the institute. But I wanted to apply this to robotics and control. Um, and and also at that time it wasn't very clear. So the learning rules were kind of a bit fishy. It wasn't really clear what the systems were optimizing for. And at the same time, these articles about dynamic programming and Q learning and how they relate to reinforcement learning became popular. And then when I saw this, I was immediately thinking, this clicked immediately. I said, yeah, okay, this is the way one needs to do this, or I want to do this, because there's a clear optimization framework. You know that at least theoretically, in the limit, you converge against the optimal solution. And that was basically what I wanted to do in my PhD thesis.
Just wrapping up mine at the moment, but we won't get into that. But so after your PhD, you started working on mobile robots, and you started entering RoboCup. For people that don't know, is where you train robots to play the game of soccer, and you can compete with other teams and other universities. Can you tell us about what it was that started to draw you to hardware and robots?
So robot was originally the robotics was originally the topic I thought I wanted to do with computer science, to apply computer science. So going into this neural networks and learning was kind of a bit of a detour,
Right.
which fascinated me more at that time. So basically going back and then
Not a
knowing,
big detour.
yeah. So going back and then applying this learning to robotics, that was kind of always in my mind. So also in my PhD thesis, I applied reinforcement learning to the cart pole system and
Mhm.
also to a mobile robot avoiding obstacles and thinking how to model this correctly so that the algorithms had a chance to converge, and then using neural network to learn this policy. So this was basically something I wanted to do, not necessarily with real robots, because I had so much experience, at least, that I knew real robots are really hard.
Hmm.
And so we started off with Simulation League in RoboCup. Again, as one area where you can say, okay, this is a competition. Universities of all around the world are competing. If you, with your methods, you can prove that you can play the game well. You don't need to explain and convince people that this is good for something.
I watched some of the YouTube videos, the both the sim and the real one as well. Um, and you obviously spent 10 years competing in RoboCup, and your brainstormer teams won 5 world championships. Um, yeah, is there anything you want to sort of touch on in over that time, and how you're able to be so successful?
Yeah, I think success came only slowly. That's why we stayed in the field for 10 years. We had to, because we only got success after 7, 8 years, or being really on the top or winning the competition. So the first year, I was very naive, and we lost horribly. And then we started to build a team also with students. Second year, we had high hopes, but also didn't make it to the final round. And then after that, we very often became second and third. And I was quite happy because it showed that our methods worked and we are on the right track. But uh, it's like in sports, the second place doesn't count. The only question that you get is what did the winner made better than you? And this
Yeah.
is a question that is really, really annoying, because you put in actually so much work, also engineering work, programming work in these, with a lot of students. And then, of course, you want to win. And we started to win then in 2005 for the first time in Simulation League. And then we also had a really good team in the mid-size league and the championship in Germany. And we were happy to win this with a middle-sized league. So these were then where it really showed off that all the sweat and tears that we put into that work finally paid off.
It would been pretty exciting watching those robot games live. Even when you watch it on YouTube, like the technology back then, you can like if it the pace is not like people might be imagining robots sprinting around the field. It's definitely definitely not that. Yeah, that's awesome. Just out of curiosity, did like at the end of each competition, did the different universities and stuff would they sort of open source why their learnings and all those things like that, so that everyone would get better, or was it kind of did the teams kind of keep their secret sauce to go into next year? What was the sort of culture?
No, the idea was, of course, to share the information and to at least report about your techniques and your thinking. With open sourcing the code, in particular in Simulation League, that was a bit of a two-sided sword. Because on one side, of course, you allow beginners to be competitive from the beginning, but on the other side, also for teams that work on their code for years, because they have a certain idea, being forced to open source their code is probably destroying their long way path, and it also kind of makes competition a bit weird if someone just takes the code from the last year's winner, which
Yeah.
is still pretty strong, and enters the field and becomes fifth or so, whereas other teams that do all their programming by themselves are only entering 10th or so. That seemed unfair. So it was always a debate whether it was mandatory to open source, and at the end we decided not to do so.
You had to
But
publish
just
papers and reports on the.
reports exactly, and people and teams that wanted to open source could do so, and we did this in later years, but it is completely voluntarily at that time.
Maybe you just open sourced your code from like 2 years ago. It's
Yeah,
like
exactly.
T minus two or something, like some buffer.
Yeah,
um,
and I think the most thing that make the most progress is that if you see other people playing, and then they are finding how to exploit the rules or make the robots better. What aspect of this very complex problem of building soccer robots can be exploited most, like a strong shot, for example, instead of dribbling, or playing passes instead of dribbling, or so, to find the right things.
the right
Uh,
policy.
just watching, yeah, helped a lot to evolve the field very quickly.
So during your professorship, you worked a couple of different unis and a fair few different problem spaces. So autonomous cars, robots, industrial process control, working with raw visual input data, games. Can you sort of talk us through that time and sort of how your interests and passions sort of evolved throughout that period?
Yeah, so the at the core of all this was always to understand reinforcement learning better, because as you said, I think you mentioned it also at the beginning, watching a system that learns something that where you yourself do not have the idea of how it can be solved is totally fascinating, and this is, I think this is still something that is fascinating until today. And then watching the learning curves to get from millions of samples to a couple of thousand of samples is also very fascinating and very motivating. So kind of reinforcement learning was also always on the basis of everything that we did. So, and then at the same time, of course, we were in RoboCup, and this basically was 80% of what my team was doing, keeping the robots, understanding, also like learning about how vision is hard in the real world, and all that kind of stuff. And then kind of seeing in advancing the robotics field, seeing where the problems for reinforcement learning might lie in the future, and then kind of going back to the theory board and thinking what can we improve in order, for example, to make reinforcement learning more data efficient, so that it can actually be applied in the real world, because simulation of complex robots is really hard and not totally understood for some kind like the dribbling a ball on a real soccer robot that you've built by your own. Building a simulator that is accurate is already a PhD thesis for
Yeah.
itself.
Yeah. So you then went on to join forces with DeepMind, working on the Atari team, which, I mean, you kind of alluded to it before, which was kind of the beginning, I guess, or the blossoming of a whole new field, which was deep reinforcement learning. What was that experience like?
Yeah, that was an amazing experience because it was exactly on that path that we wanted to go to bring reinforcement learning to the real world. We started to do deep reinforcement learning in 2007, 8 with a PhD thesis of Sascha Lange in my lab. We had continuous control, bringing reinforcement learning control to continuous domains with a PhD thesis of Roland Hafner. So it was clear that there could be a path to actually bring it to real world control applications. And I always kind of this, I 20 years ago, I always declared this as the goal of my life to at some point bring reinforcement learning in a real world application. So when DeepMind approached me, Shane Legg and Dan Wierstra approached me at ICML conference and told me about this idea. Let's join forces. We think that reinforcement learning is good enough now, and we know a lot about supervised learning. So it's the right time to now take it seriously and bring AI to the world. I was immediately saying, "Oh wow, this is a big vision. I always wanted to work in a startup. These seem to be the right guys." Then I met Demis Hassabis in London and heard about his very ambitious and inspiring plans. So for me, it was a no-brainer that I really wanted to join this company if it's possible.
So there was obviously a few big sort of breakthroughs over that time, obviously like deep Q networks, learning from raw pixels, experience replay. Why do you think some of these steps were so important to the field?
Yeah, I think before that, nobody had actually thought that it is possible to have such a general learning system like we have shown in Atari. Raw pixels in and actions out. That was for a field that was mostly occupied or mostly busy with solving mazes. That was kind of a huge step forward. And then also the idea that to use replay buffer to be more data efficient, that I think that is also and still is a very important research question because not everything can be simulated. And at some point, if you want to have something that is truly intelligent as humans, then data efficiency is a key because also if you think about it, we call people intelligence if they learn very quickly, and this means that they are data efficient. If someone takes 50 years to learn to write numbers, we wouldn't say probably this is also better than a dog will ever be, but we will not necessarily call this a particularly intelligent human. So data efficiency is what I think at the heart of um, of of intelligence, and DQN was kind of taking this thread from the NFQ algorithms that we developed in our lab and brought this also to a broader audience.
And then I think you touched on it before, but around that time, obviously, like within the whole Atari project, there was the generalization breakthrough, which what you talked about before. What did you think that specifically meant at the time? So that ability to have one sort of algorithm that could solve, a whole bunch of different Atari games, right, and get
Yeah.
better than human or human performance on all of them.
I think that was also a really important point because up to that point, people were looking at certain applications and then saying, okay, what is specific about this application? How do I help with, for example, a certain reinforcement learning signal, a certain reward signal? How can I shape my reward signal? What features
Very
do I
manual.
need? All manual, yeah.
Yeah.
And then with Atari, it was really the proof of concept. No, the only thing that from the outside is basically a reward signal and one algorithm, one architecture, and you can learn all of this with one single thing. And I think this was also a very important message that was given with the Atari project. Basically, that something like AI or AGI is possible, at least in principle, and not only a dream.
Mm. Just so for my questions, do you have a hard stop at the hour?
No, no, I can go over time a bit.
Not too much over. I was wondering if I need to rush through or not. But
No, no,
I
no,
get
no, it's fine.
you touched on it just before as well. But I guess what was it like to join forces with so many other sort of powerhouses in your field? Like, what impact did that have on you personally and your growth?
It was definitely very inspiring, for example, to meet people like Demis, who had the very clear idea what to do and what they want to achieve and how to achieve this. Actually, approaching the right people to get the right funding, having the right ideas of how a company in 2 years, 5 years, 10 years could look like that is working on AGI. Problems that might arise, like the ethics aspect of AI that was there from the very first beginning. So this was kind of people that are thinking really big and not just in the next paper for the next conference, but having a lifetime mission and also not just claiming that they have it for example, to raise some money or some funding, but really believe in it and actually going for it. And then also I remember well when I came to DeepMind at one of the first occasions, then people were already waiting for me at the whiteboard and saying, "Oh, Martin, it's good that you're coming in." I was just coming in from Germany, standing up very early in the morning to get the very early morning flight, and then first question, I have the following question, and then starting to write. So this energy of I
Yeah,
want to know, and then I want to implement this, and I want to see. So this kind of spirit that I really appreciate it, and then also people that where you only have to explain it once and probably only in a very short sentence, and
yeah,
they
yeah,
immediately got the message and they
yeah,
start acting on it. This was
yeah.
a
Awesome.
very game-changing moment for me.
So after you joined, Google then sort of acquired DeepMind. What was it like to go from that sort of startup research group to working under the Google umbrella?
So I think for me it didn't change a lot. So we always tried to. Demis was very keen also to try to keep the spirit of this company, to make very clear that we are on this long-term mission and what that we really want to solve AI. And he took care a lot of also of these organizational efforts. So for me, as a kind of leading a team, it was basically the same message, like focus on your research, try to make progress on that, try to be make world-class research. And whether it was under the hood of DeepMind or later under the hood of Google, that for me personally didn't change a lot.
Change. Did anything change in terms of like enablement? Like obviously, a whole bunch of free compute isn't bad, but did they also, did they give you guys like teams of like cloud developers or architects to sort of handle all your sort of ML operations, ML ops stuff, so you could just focus on the research?
I think that was also already there in the
Already had
DeepMind
that.
mission. So we had stuff that were looking for organizing social events, for example, that were there for helping with the engineering stuff to set this up. Of course, in when we joined the Google world. Again, I didn't notice too much because for me it was already working, but things probably got much more professional and faster and having access to much
Yeah,
more compute than we had before. But again, for me, it wasn't so much of a
didn't
change.
change.
was more a change for the development of the company as a whole, as an organization.
So, in the paper Deterministic Policy Gradient Algorithms, Silver proposes a new class of algorithms for dealing with high dimensionality continuous action spaces. And I guess through this vein, DeepMind were then able to expand the potential applications of reinforcement learning to include more complex real world systems that, like robotics and autonomous vehicles, that had that high dimensionality action spaces. Can you talk to why this was such a critical step for the field?
Yeah, I think in general it wasn't very so reinforcement learning with discrete actions like they were used in Atari. This was basically known, and there was already a lot of work. How to do it with continuous action was kind of not clear, also because then it also has questions on the theoretical side. Um, but we came up in the PhD thesis of Roland Hafner with an idea of propagating the gradient through the Q network in order to adapt the policy, which was basically an intention of the neural fitted Q algorithm called neural fitted Q for continuous actions, NFQCA. And the work from deterministic policy gradient that built basically on that idea and showed that it's theoretically sound to do so. Um, and then, of course, in all the robotics, why it's important, in all the robotics applications or classical control applications, you want a continuous control signal, for example, to change the voltage or to change the steering wheel or whatsoever. These are typically continuous actions. And with that, you could show that basically there's the principles are the same. It's only about adapting the policy according to the Q function and bringing this somehow to the continuous policy.
And how do you think, like, being able to make that leap from discrete action spaces to continuous action spaces, I guess, and all the different problem spaces that open up with that, how do you think that affected, I guess, the pursuit of, was it you that coined the term AGCI, artificial general control intelligence? Yeah.
Yeah.
So maybe if you want to just say what is AGCI, and then how you think that sort of leap from discrete to continuous helped in that vision towards AGCI.
Yeah, I think the general term AGI is clear, to have human-like intelligence, which is then all from being able to compose music and solving maths problems, talking and so on. And whereas what I was kind of particularly interested is to understand these low-level controls, like what makes a human or a baby to start to learn walking. How can they learn to learn walking? How can they learn to grasp objects? How to assemble objects to bigger compounds and stuff like that. So all these motor skills, which I found really important, and as a field is really important. I think from the perspective of AGI, understanding this low-level controls is a really important step. That is not just a nice to have, but it's really crucial, because this gives you the grounding in the world finally. And also because I think the principles probably also then transfer to these higher levels, like learning language later on. And on the other side, also this focusing on this control side of things, this obviously also opens up a whole industrial field, like controlling robots or controlling all these this dynamical systems that are out there. And therefore I thought, okay, to make clear that we have a particular mission in the control team, we need to coin this term, and this is AGCI basically.
I like it. I really like it. So obviously I'm interested in coming from a robotics background, interested in seeing reinforcement learning on real world systems as well. Probably one of the more higher stakes use cases you could work on would be, I don't know, a nuclear fusion reactor. So just to make it more exciting, you could do that as a zero-shot learning problem. Can you tell us about that project and what that was like?
Yeah, so it started as a challenge. We, as a control team, were always looking what we could do besides robotics,
Mm,
because it was always meant to be much more broader than just doing some stuff with robots. And then we had this opportunity to collaborate with EPFL, the university in Lausanne, who had actually a tokamak reactor.
mm,
And they were interested to actually collaborate with us on some control problems. And so, yeah, it was immediately clear to us that this is a huge opportunity to show that reinforcement learning can do something good, first in the real world, and then
yeah.
also for if fusion turns out to be working, then for the benefit of humanity, and then being at some of the core parts of this technology is of course an amazing story that fits nicely to this DeepMind overall story. And we were lucky enough that we had very interested and also very capable collaborators at EPFL, and therefore this project could develop over two and a half years, and finally actually being applied on this real world tokamak to control the plasma inside.
Um, can you tell me what it was like when you did the first zero shot test? Like, what's going on there? You guys nervous? Like, what's the feeling?
Yeah, of course, you're nervous. I think first of all, you are aware that this is a multi-million euro device that you're now controlling, which is very precious to all the physicists that are doing serious work on that. Uh, and so you really want to make sure that no matter what the reinforcement learning controller does, you cannot destroy this device. But we were reassured by Federico that this couldn't happen. So this was a good thing. And then on the other side, of course, you spend a lot of time modeling it and in getting the learning algorithms to work. And then if you apply zero shot, you have no control about this. It just either works or it doesn't.
So I know that there was obviously safety systems in place, but I thought that the algorithm originally used like a control input that it wasn't meant to. Wasn't that right? And it made the machine sort of shake or vibrate or something along those lines.
Yeah, exactly. It was using coils that were meant for something completely differently, for something completely different,
Yeah,
and it misused those coils because it could also stabilize the plasma, and it
yeah,
figured out that it's probably more convenient for it to do so. No human would do it because if human
yeah.
would develop a controller, they have this in mind. Never use these coils, and
So they
so it
told
was
you that
fine.
they said stop doing that.
Yeah, the system was fine. It was still safe, so there was no danger for humanity. But of course, it was if we would apply this policy more often, then it could have mechanical consequences at the end, and you would need to repair the device that we didn't want. So we did applied it once, and then when they said, "Oh, please do not do this again," we changed the reward functions accordingly and set some constraints, and so this never happened again.
And just obviously in that particular project, they have quite a high fidelity simulation. I guess how important was that for you guys? You know, given the fact that it's a zero shot learning project, and I guess was the simulation ready to go when you guys came in? Like, could you just use it as it was, or did it have to be improved? Like, what was the state there?
So you asked me for the first experience with the zero shot transfer, and the first experience was, of course, nothing worked. So the plasma appeared, and we took over control, and it was directly destroyed. So because the zero shot transfer didn't work at the beginning, and then
Mhm.
you really go into what was wrong. Is all the wire? There are simple thoughts like: is the wiring correct? Is the control messages that you give? Is this exactly going to the same coils than in simulation? And of course, it wasn't, because there was some changes there that nobody was aware, or people forgot, because it's everything is really complex. And then after you fixed that, then you go to the next step, and then probably you could hold the plasma for a couple of steps, control steps, which is less than a millisecond or so, or
Yeah.
maybe
Yeah.
5 milliseconds. And okay, something is working, but we're far from being there. And then, of course, the simulator is changed. The noise that you inject in the simulation, because you are never sure, you are sure that the real world doesn't match your simulator perfectly, and what you're doing is you randomly disturb the process, so that you, even if your modeling is wrong, then you code for a
Yeah.
broader range of modelings.
So you injected stochasticity into the sim, but was it random, or did you base it off like measured stochasticity in the real system?
Yeah, it was both. So some things you just have a range. For example, for we are not sure how large the delay from actually the system has controlled has computed the control signal to when the control signal actually arrives at the plasma or at the coils, because there's always a delay in these real world systems.
Yeah.
And then for that, you can, for example, assume a certain delay, and you want to make sure if the delay is between 2 cycles or 5 cycles, you're still good to control. So there are things like that. And then other things where you want to have more stochasticity in it, with noise in sensor values or so. So there are different ways to cope with different types of uncertainty that you have in such complex physical modelings.
Just in obviously, like, it's a, I'm getting the feeling you love, or you really get up for these like big sort of grand challenge projects. What was it like to work with sort of other experts in different fields, like working with the nuclear physicists and all that? What was the ways of working? Did you guys co-locate for the whole time? Like, just wondering what the keys to success were to sort of collaborate with other experts in this type of a project like that.
So yeah, we talked a lot. Of course, they were in Switzerland, we were in London, and then also COVID kicked in after some time, which didn't help either for faster communication.
Yeah.
But on the other side, also like communicating regular communication by the video conferences is of course very important for these kind of projects. Having regular stand up. Being sure that everyone in the project knows what they're doing, and then having an amazing team. I really keep saying that for this team, there were every expert in their own field. If they haven't done an excellent job, projects like this are not possible. If you don't know what to do on the reinforcement learning side, then it doesn't help you to be an excellent nuclear physicist. And on the other side, if you don't know where nuclear physicists, where the simulator may be flaky, the best reinforcement learning algorithms will not work on the real plant. And so this was or people that are just making the neural network so fast that it can work on 10 kilohertz. They need to be experts in their field. Otherwise, you have a possible perfect policy, a perfect simulator, but your controller is too slow. And so this is an amazing example where some things are only possible if you really have very excellent people, and they
That's
will be
why
very
you had
good.
to have in the actor critic, the actor was obviously a much more compact neural net compared to the critic. So you've done a lot. Well, I'm not sure, but you've done some work in technical process control as well. And you sort of mentioned before, obviously a wide range of control problems is your interest. What untapped potential do you think lies in process control? So, for example, like, chemical plants, LNG plants, or hydrogen plants of the future?
I think there lies a lot of potential, because what reinforcement learning allows you is really going for the optimal solution, and not by having a very careful analysis of the process and understanding all the dynamics and the nonlinearities, and then understanding how to make them linear so that your classical control methods work, but really by learning just out of the data that you observe. And so this technology could have a huge impact in systems that are not totally understood, where you really want to get to the optimal process. One example could be automotive engines, where you really want to get the best out of your fuels. And currently, engineers are turning their knobs with all their experience. But what if you can learn all out of that by just observing how the engine actually behaves, and then improving over time? So yeah.
I think so. Obviously, with the nuclear fusion one, like one of the reasons that RL can excel in that place is because handcrafting one of the control algorithms traditionally for that system was, so manually intensive, right? Now, a lot of these other fields in like process control, for example, have been or use traditional control or traditional optimization techniques, for decades. How do you go, or how does your team go about exploring and assessing whether or not RL can add value, any further value in this particular control setting? Whether it could actually outperform traditional control techniques, for example. How do you go about assessing that?
Yeah, I think the best way to go about this is like we did in the fusion setup, to work with experts that have their control method, and they really believe in their control system, and have gone to the limits, and then say, okay, let's challenge that. Let's see whether we can get something additionally out of that. And in the fusion, in this first project, it was clearly that we probably will not come and say, okay, we have the best controller in the world, and we are much better than everything that you have done before. But
Yeah.
just so there are different ways, and the next step then could be, okay, probably there's also different objectives that are too difficult to handle with a PID controllers, or that are probably better handled if you look at the entire control system, this 18-dimensional thing, as one, instead of having individual PID controllers for every single coil, and stuff like this. But this actually, you can only do this by going into the field and proving it on some application, and show, look, this is what I can do with a reinforcement learning controller. Now show me what you can do with your classical controller. And there are definitely, I'm not saying that reinforcement learning control is better in all respects. There are a lot of open questions still. But there could be some things that you can probably solve better with reinforcement learning controllers than with a classical approach. But the proof is in the pudding. Yeah, you actually have to, or the proof of
You
the
have to
pudding
do
is
it.
in the eating.
Yeah.
Yeah.
Craft the right experiment to do it. So I'm just going to move on to some more general questions now. There's been a few AI hype periods. You've probably been or lived through a couple of them. Do you think this time is any different? The era that we're in right now.
I think it's
That was a
different
big
in
sigh. That was.
I think it's definitely different in that it's a really big hype. There are really high expectations. The things that we are seeing currently, like from these large language models, are things that also overwhelm experts. If you had asked me 5 years ago whether this is possible, I clearly would have said no to the types of generalization that we see that come out of that. So it's also some of a qualitative leap that we're currently seeing. With all hypes, I think that's some lessons that you can learn from the past is probably at the beginning it's overhyped and everybody thinks now everything is solved, and then after some time it's probably going down, then people think, oh, maybe it's not so beautiful, and then they underestimate what will be the consequences long term. And I think that's probably in that respect, it's a hype like many others that we've seen before. What I, as a scientist, find interesting, that this is something that now really very quickly got public interest, and this is definitely interesting from all the other hype I've seen in science, like going from neural networks to support vector machines. Nobody noticed in the real world that this was a thing.
In the real
This
world.
time it is.
I love that, the real world and the AI community world. So you touched on it just then with the LLMs. Obviously, there's been a bit of a shift in focus in the community. I know that you've mentioned that to understand how humans build up behavior from raw experience is really important, rather than just absorbing sort of large corpuses of data. And that's sort of critical for getting towards understanding intelligence. As you said, the LLMs though have demonstrated these unexpected generalization capabilities. Now, I've sort of read online, and it's called, I suppose, the scaling effect, which some researchers have also called a bitter lesson, which is the idea that general methods leveraging enormous compute and enormous data could or can outperform methods or models that rely on sort of more sophisticated methods or sophisticated reasoning. What is your views on the scaling effect, and how could the scaling effect affect other things like reinforcement learning or domains outside of language?
Yeah, that's a very quick, a very good and a very tough question at the same time. I think the scaling effect in language, that is amazing, and this was for me and probably for a lot of people in the field, that was also unexpected, and of course there's good reason to believe that if we apply this to more raw data that is not as organized and as structured as language is, then we are able to see similar effects,
Like maths.
like math, or like also in control. Like, are we possibly able to come up with, if we only put in raw data, are we able to come up with reasonable physics models in such large models, just by putting in raw data, and then you apply supervised learning, and it just happens that you have a deep understanding of the world and can solve everything. I think, of course, there's there's evidence to believe that, and we should absolutely test this. I'm a bit more skeptical, and there I think there it comes into play. I also can totally think this is a nice argument to say the bitter lesson is, at the end, it's only the right algorithm and the right model, and you can go a very long way. All this modeling is probably not needed. But the big question is, what is the right algorithm? And will we find the right algorithm if we don't do modeling? And the models that we have, these transformers, they also are an evolution, because we have gone through a couple of other lessons, like convolutional neural networks and knowing how we can represent knowledge. And if we don't not do modeling, we probably have no idea how to get to these simpler models at the end. So just saying, oh, take a very simple algorithms and then more compute, that will not. I'm pretty sure that this will not give us or get us all the way to AGI. So some simple algorithms and some simple model tricks are still missing. And until we find them, I think it's a fair game to also think about a bit more modeling and then reduce this model to really go down to the principles. So although I believe I could potentially believe in this story, at the end it's probably very simple or very principled and simple, and it's only compute, and this will work. I can believe in this because our brain is probably a very simple system. It can be reproduced, obviously, so there seems to be some kind of robustness and simplicity. But to find this, to just say, oh, I take a very simple algorithms, a lot of compute, and a large model, that is definitely not going to be the solution.
No, I agree. So back in ICML 2017, Peter Abil, if you know him, gave a keynote where he showed a P2 robot doing a wide range of dexterous tasks, so cleaning a sofa, rearranging magazines, picking up Juco blocks, and finally, I guess what we'd always want in our household, robot who cracked a beer. Um, and I remember that keynote being really big because everyone in the audience thought that there'd been some huge AI breakthrough. But really, the robot was completely teleoperated the whole time. Um, and he then went on to sort of challenge the machine learning community, by saying, physically, the robots that we've been building for decades now are perfectly capable of performing a wide range of useful tasks. The challenge is that we cannot embed them with the required intelligence. And therefore, creating useful state of the art robotics is a software challenge and not a hardware challenge. And that is a challenge that should be being solved by us, this community. I love that. I love that moment. But over the last few years, especially, there's been an explosion of interest in the research community in the intersection between robotics and machine learning, and even that's heated up, over the last few months quite drastically as well. Boston Dynamics releasing the new Atlas robot. There was the video that went viral of that Figure AI robot doing the dishes. Even I think like 2 days ago, I watched the video of the robot dog learning to balance on the exercise ball. I'm not sure if you saw that one, but yeah, I'm personally struggling to keep up with it at the moment. But it's obviously a very exciting time for robotics. In your view, what are the fundamental principles or breakthroughs that you think it will take to enable robots to perform, a wide range of useful autonomous tasks, complex tasks? Like, what do you think the key steps, the key breakthroughs that we need to get through? The
I think
context
for me,
there.
yeah, we, I have also a lot of debates with my colleagues. For me, I still believe that understanding how to data efficiently learn by itself from data, that is key.
In
So
complex
reinforcement
environments,
learning,
especially, right? Like data efficiency in complex environments.
data efficiency in complex environment. Yes, how to kind of understand that how the robot can build up very simple experiences like touching objects, then to grasp objects, how to build on this knowledge from the beginning, first of by reusing this experience, but also by finding some internal way how to scale up this kind of this knowledge. One way would be to use skills and to build more and more complex skills in
Mm,
a scaling way, not just building one layer of skills and then showing that it works. There's a lot of work already outside, but understanding the principles, how these skills are formulated, how these skills are found and how they are reused. I think that for me is still an important question on this path. There's also, but on the other side, there's a big trend of people saying we just need to do better teleoperation and then copying it and throwing it then to systems like large language models or similar systems that already have some prior capability of generalizing, and then everything will be solved more or less by generalization or interpolation between these policies. And I think it will be very interesting to see how this debate will go in the future when these
yeah,
when the stages to get out of this. I show a cool video on YouTube to now I'm in the real world and this robot has to work
yeah,
100% all the time. So
yeah.
that and there we will see what is still missing and where the important things are.
Um, if you could talk to a younger version of yourself starting your career today, what would you tell yourself?
Repeat.
That's the best answer, isn't it? That, yeah,
No, I think, of course, there are always decisions that you could make otherwise. On the other side, I always try to ask myself in every stage of my career if the things that I'm doing currently are the things that I think or that make me happy and are fulfilling in some sense. And for that, and I know that I did that, and it kind
Yeah.
of worked out, and I feel happy at the position where I'm currently at, and therefore trying
Yeah.
a different path
That-
would be interesting. But if I had to put, if I really had to risk it, I'm not
yeah. Yeah.
necessarily
It's
doing
like
it. I don't know.
the butterfly effect, right? You don't want to change change anything.
Yeah.
Um, so um, if you were to retire today, what aspect of your career would you be most proud of?
I think it's probably RProp, neural fitted queue, and the stuff that we did in RoboCup with
Mm,
the team. Yeah, and this is on the scientific side. On the personal side, I'm pretty proud that I still have a very good contact to most of my previous students. Um, they we talk and we have fun when we see each other,
mm.
and this is also an achievement I'm pretty proud of.
Yeah, that's awesome. If you could interview anyone the same way I just interviewed you, living or dead, who would it be?
It would probably be Barack Obama,
Oh, okay.
which I find very interesting. I think politicians in general, I think, are very interesting persons, putting so much effort in something to change the world, and getting also so much negative feedback for the things that they are
Yeah,
just they which just lies out of their hands. So
yeah.
I think that I'm
A
quite
president.
fascinated by
Yeah.
politicians.
Um, will we ever see you working on an autonomous control system for extreme mountain biking?
Whether I would like to, or
Yeah. Well, will we ever see that one day? Have you ever thought about doing that?
and this is also really a good question, because not necessarily mountain bike, but for skiing, we actually planned to apply for a European grant at some point to build a skiing robot that could learn completely for reinforcement learning. Back in the days when we were trying to combine this kind of tedious way of writing or applying for grants, but then getting the most fun out of this. And I had a couple of people to whom I talked whether they would also be interested to spend six months in the year in a skiing area, uh, and doing some cool work stuff, and having a good leisure plan at the same time.
It'd be uh, it'd be interesting to see how the vision models would deal with detecting moguls, like the little, we call them moguls. Is that what you call them? Like little dips and the bumps.
Yeah, yeah,
Because like
absolutely.
some days you can't see them like at all. Like it just
Yeah, that's right. Yeah,
it just
yeah.
looks
You
all,
would
yeah.
probably be more free to have sensors in your skis. Uh,
Yeah, at the
so
tips.
at the tips and everywhere probably, so you could cheat a bit, so
Yeah.
you to extend the sensory space of such a device.
Last question. If you could only recommend one book to somebody, what would it be?
Ah, scientifically, I would probably say Kahneman, Thinking Fast, Thinking Slow.
Yeah, I love that one.
Otherwise, there are a couple of books. There's a German writer, Hermann Hesse, who wrote Siddhartha. It's probably not, I don't know if this is known internationally.
I haven't heard that one. I know Daniel Kahneman, Thinking Fast and Slow. Yeah, that's a beautiful book.
And
Yeah,
also, like classical German, Goethe's Faust is really a very interesting read. I never did it as a student because I refused to read the books that were recommended by my German teacher. But I read it later on in my life, and I found it has really profound human knowledge of how life works, and this all in beautiful rhymes. So I probably could also recommend that.
it's funny. Whenever I ask people that question, I always say one, and no one ever gives one. They always, they always.
Yeah, sorry.
I don't know. It's good. Martin, thank you so much for taking the time. I know we've gone over here. Yeah, really appreciate it, and hopefully you enjoyed the questions.
Kyle, thank you very much for these very thoughtful questions. I'm really happy for all the deep dive that you took into my life, and I really enjoyed answering all of these questions. And thanks for the magic trick.
Almost got, yeah. That was.
It was
I'll
fantastic.